Good morning, everyone. Our topic is Cardinal Pill Testing of System Virtual Machines. My name is Hao Shi, and this is a joint work with my colleague Abdulla Alwabel and our advisor Jelena Mirkovic. We come from University of Southern California Information Science Institute. Current malware analysis heavily uses virtual machines for dissecting malicious software. For example, QEMU, Box, Ether, and many others. The malware authors also know this fact, and they want to detect the virtualization and escape from the virtual machines. Upon the detection of virtual machines, the malware can change their behavior from malicious to benign, escape the virtual environment, and even crash the virtual machines. One of the most important anti-VM attacks is CPU semantics attacks. This kind of attack is based on the fact that in some cases, the same instruction with the same input values will lead to different system states when executed in a virtual and in a physical machine. The other two important attacks are timing attacks and string attacks. We have observed the increasing popularity of anti-VM in recent years. In the area of testing system virtual machines, we define a pill as the combination of instruction mnemonics plus the register and the memory parameter ranges that lead to different execution in a virtual and a physical machine. Our goal is to enumerate all the CPU semantic differences between a virtual and a physical machine. Here, we also call a physical machine an oracle. And then, after we have all the cardinal pills, we can lie to the malware with the expected values for oracle. Here is the quick view for our evaluation. First, we find 5 times more pills by running 15 times fewer tests than related work. And second, we analyze the root causes of cardinal pills. Third, we find most of the pills stem from the kernel registers. And finally, we can enumerate all differences between a virtual and a physical machine for selected instructions. Our work is mainly built on 3 related work. All of them come from the same first author. The first one is red pill testing. In this related work, the author generates random values for instruction parameters in user space. In their improved work, this work manually crafted test case templates for kernel instructions, but it still uses random tests for instruction input. And in their latest work, the hi-fi tests for lo-fi emulators, the authors use symbolic execution to translate the code of a high-fidelity emulator, which is Box. And then they generate test cases that can investigate or discover the code path. Finally, they run these test cases to test low-fidelity emulators, for example, QEMU, Ether. However, there are some drawbacks and flaws for all of these methods. First, random tests cannot guarantee completeness. In their second related work, it still suffers from the same problem, and in addition, their custom kernel cannot be generalized. In the third related work, symbolic execution cannot test floating point instructions at this moment. So this is the main drawback. And this paper compares 2 virtual machines, which is different from comparing a virtual machine and a physical machine. If these 2 virtual machines have the same defects, their test will fail to find these differences and thus corresponding pills. So this is the overview of our testing architecture. Basically, we have 3 workstations. The left side is the master, and the right side are 2 slaves. In the master side, we install WinBag for debugger, and the master stores test case states in various testing phases, which I will explain in next slide. And finally, the master will compare states to determine if a test case is a pure or not. On the slave side, both of them store the same set of test cases. And in addition, a daemon that helps communication between the virtual machines and between the master and the slave is also installed. Here, we define the system state as all user and kernel registers, the data stored in the part of code, data, and the stack segments that test cases read or write. Our logic execution for each test case can be divided into 4 phases. In the first phase, the master issues a test case name to the slave. And then the daemon inside the slave will load this test case and then notifies the master. When the master gets this notification, it will store the raw state of the slave and stores the state in its local storage. And then the test case performs initialization work and notifies the master again. In the third phase, the master stores the initial state and releases the slave to let it run freely. At this moment, the test case will execute in the real testing instruction in testing and notifies the master again after this instruction has been executed. So in the final 4th phase, the master will store and compare the final state of each test case and determine if this test case is pure. Okay, so our goal of system testing is to generate a minimum set of test cases for each instruction that can explore all code branches. So we start from the Intel manuals and analyze 2 kinds of behaviors. The first one is defined behavior. This means that the Intel manual has exact semantics for each instruction. The second category is undefined behavior. This means that the Intel doesn't say anything about the flag bits each instruction should update or read or write. So there is no standard answer for the undefined behavior. It is changed based on some undocumented ways. So in order to achieve our goal, we basically use 3 methods to achieve our goal. The first one, for defined behaviors of a given instruction, we need to evaluate all branches. And we consider all flag bit states that are read implicitly or explicitly or updated using results. The second, we will evaluate all exceptions raised by each instruction. And third, we also investigate undefined behavior and try to find undocumented implementation specifications. We basically group all the instructions in the Intel manual and classify them into 5 broad categories, which are arithmetic, data movement, logic, flow control, and miscellaneous. For example, in the arithmetic group, all instructions in this group first read some arguments and then perform some arithmetic operations. For example, the add, subtraction, multiplication, and so on and so forth. And in this group, we combine instructions that read or write the same register with similar rules into a smaller partition. And we generate test cases based on the partition level. For example, for the test cases generated for this partition, we consider the minimum value, the maximum value, the boundary value, and the random values within each different ranges. If necessary, we also flag the EFL register bits to test each instruction. Here is the overview of our evaluation. Basically, we generate around 20,000 test cases in total. And we use 4 different QEMU virtual machines. Please note that we test QEMU in 2 different modes. The first mode is tiny code generation mode. In this mode, QEMU translates the guest instruction into host instruction in pure software. The second mode of QEMU is VTX, which is assisted by Intel hardware. This mode can achieve high fidelity. We also test a box and 2 other physical machines. Here is the overview of our results. The first column shows the different virtual machine versions. The second column shows the number of peers and the corresponding percentage out of the 20,000 test cases we have. The third column is the crashed test cases. This category means that these test cases crash itself or the system, so we have no way to save the final state, so we have to discard them. And in the final column, which is the fatal test cases, this means that in these test cases, the virtual machine and the Oracle give different initial states for the test case. So we cannot use them for final Cardinal Pill comparison. Please note, although Intel VTX provides high fidelity, the actual performance still depends on how the hypervisors use this hardware assistance. In addition to count all the peers, we also compare the quality of our peers. First, we compare the yield rate. For example, the total test case and for ME-fuzzer and hi-fi, lo-fi, they need a high number of test cases. But for our Cardinal Pill testing, we only need around 20,000 test cases. For the peers found, about 7% of total cases in ME-fuzzer is peers. And this number is about 10% for chemi-fuzzer. And in our testing, this number is almost 50%, which is a great improvement over the related work. Second, we compare the unique peers out of all the peers we find. The unique peers means that these peers has different parameter values read by each instruction. For ME-fuzzer, this number is 9% of all the total peers. And for hi-fi, lo-fi, we don't have the data set from them. And in our testing, this number is 100%. This is the direct benefits from the novelty of our testing method. We also compare the unique mnemonics. ME-fuzzer finds less than 200 unique mnemonics. But in our method, we find more than 600 different mnemonics, which is almost 4 times. So after we find all these peers, we move to analyze the root causes of peers. For the root causes listed in hi-fi, lo-fi work, we find both peers in general purpose instructions and peers due to QEMU's memory management unit. But we don't find peers in kernel instructions. This is because we do not extensively test kernel instructions due to the extensive time needed to reboot the system. And we leave this for future work. However, we find some more important new features of QEMU. First, QEMU failed to update the flags and masks in floating point control register. Second, we also find that QEMU failed to update floating point status register. And sometimes QEMU just failed to throw some certain exceptions when it should be. And in other cases, QEMU also failed to update floating point tag register, floating point instruction pointer, and data pointer. For the detailed list, please refer to our paper and our website. For the undefined causes of pills, the only source is eFlags register. For this kind of pills, we generate additional test cases to explore the semantics of modifications to undefined resources in each processor. A flag may be modified in 4 different ways, and we need to find how the processor uses each different way to modify the corresponding flag bit. Understanding the semantics of undefined resource modifications will help us devise hiding rules without exhaustive testing. And here are the takeaways from our work. We propose a Cardinal Pill testing, which needs moderate manual effort to analyze instruction in a manual. And then we automatically generate test cases and identify pills from the final system states. For the completeness, basically, we have 3 main claims. First, we claim that it is complete for pills for user space instructions that affect defined resources. Second, we claim that it is complete only for a given virtual machine and a physical machine pair of pills that affect the undefined resources. And finally, our testing for kernel instructions is incomplete because we didn't test them extensively. After finding all the pills, we also propose a way to modify the QEMU source code and avoid these pills. Please refer to our paper for more details. So thank you for listening. Any questions?
So again, if you have questions, please come up to the mic and state your name and affiliation.
Hi.
Hi.
I'm Eric Ide from the University of Utah.
Mm-hmm.
So I read your paper, and I had a particular question. So you said that you tested 4 versions of QEMU, right?
Yes.
And those versions included 1.6.2 and 1.70, right?
Yes.
And you identify those as Q3 and Q4 in your paper, right?
Yes.
But your paper doesn't present any data for those versions of QEMU that you said that you tested. So am I supposed to conclude that you didn't find any pills in those versions of QEMU?
Yes, we do find, a quick answer is we do find this, wait a sec. So please look at the first column of the virtual machines. Due to the space limit, we only present 2 versions of QEMU, which are labeled as Q1 in TCG mode and Q2 in TCG mode. And all of them are also tested in virtual technology extension world. We do find pills for all of the 4 QEMU versions, but we just limit 2 of them. And for more details, you can refer to our paper for the detailed numbers.
Well, this is what I pointed out, right? Your paper that appears in the proceedings doesn't have any data for Q3 and Q4. So perhaps I could find that data at your website?
It's published in our paper. Yeah.
Okay. I'll look again.
Okay. So.
All right. The second question is just in general. Do you find that QEMU is getting better over time or not?
No. QEMU didn't get much better. Only basically, I don't remember the detailed numbers, but the performance are quite the same. They didn't improve too much.
All right. Thank you.
Thank you.
Okay. Can you hear me? So let's thank the speaker again.
Thank you.